notice something quickly, trying to fix in this. When you differentiate this, since you are basically, it's square root, it's this thing to the power of 1/2, so you have to take 1/2 out. So there's this 1/2 here, and then there's this 1/2, which is here. So there's a factor of 2 missing in that expression. And it's right in your handout, so don't need to worry about that. But, so that's one thing. Now let's come back to our transistor and see what we have so far. So far, we have this GM, the transconductance of the Mosfet. We have the transconductance of this back gate transistor, sometimes that's what it's called, or the bulk transistor, GMB. And then we have the RO. And we saw that the resistance here, unless your gate oxide is very thin, is not significant. So this was the basic low frequency model. But now let's go back and see if we can come up with expressions for the high frequency part of this, the capacitors. See what kind of capacitances we have in this transistor. So let's look back at our transistor very quickly. Again, an NMOS. And so you have the gate oxide, you have the conductor, and then in the pinch-off region, you know that you have a channel across here. And this voltage on the VGS minus V. Now, what kind of capacitors do I have? Where do I have capacitors? Well, I have 2 depletion regions, right? I mean, I have 2 PN junctions. These are really like diodes. They're reverse bias diodes, but they're diodes. So I have a depletion region here and a depletion region there associated with that. And we know depletion regions have capacitors. Right? So what is a capacitance? Well, if it's an abrupt junction, so let's say C, this would be CSB, would be CSB naught, which is a capacitance with 0 bias. And we know this is a voltage dependent capacitance, so it would be 1 plus the SB divided by psi naught, which is the built-in potential to some exponent, let's say M in general. If it's an abrupt junction, M would be 1/2. Right? And a similar one for CDB. Right? We CDB naught, some junction capacitance at 0 voltage, 1 plus B dB over psi naught, again to the similar exponent. So you have 2 junction capacitors there that are voltage dependent, so they're not even fixed. They're voltage controlled capacitors. But other than that, there are 2 capacitors that I have to worry about. So where are they? They're between the drain and bulk and source and the bulk. So one is between the source and the bulk. So one is down here. So this is CSB. And then the other one is between the drain and the bulk. So it's between here and there. CB. Okay, so I have to know about those. That's fine. I can calculate it from that expression. Well, what else? Well, look at my transistor. In pinch-off region, in the pinch-off region, do I have a capacitance between here and there? The gate and the drain. Well, I do, right? Because first of all, even if the transistor looked the way I looked like the one I've drawn, there will be some fringe field. Like that. And more importantly, actually what happens is that when the way you build these things, in the thermal cycles you put them through, usually the drain and source are extended a little bit underneath the gate. There's a little bit of overlap here. Let's call this length LD, the L overlap. I'm sorry, L over overlap for this capacitance. So the total capacitance can be really captured, I mean, to the first order. Let's say if I wanted to calculate this capacitance, right? It would be what? It would be Cox times L overlap times the width, which gives me the total area of the slice that gives me the capacitance, right? So that would be the C overlap. But that doesn't take a fringe into account. Now if I want to take a fringe into account, I can have a fringe factor, fudge factor really, here, to account for that, some additional capacitance. But the way we usually do it, we actually make this L overlap the fudge factor. So we absorb that into the L overlap. When I give you an L overlap, it means that if we calculate Cox times L overlap times W, that would be the total capacitance that you get. Now, in reality, nowadays, if you look at the cross-section of the Mosfet, it doesn't look like that. today's Mosfets don't look like that. That's not to the scale. So it looks more like this. So this is the gate. The oxide you can't hardly see. It's only a few atoms there. And these are the drain source. So you can see you will have a much larger fraction of the capacitance coming from the fringe field in this case than that in that picture. But nonetheless, all of that is captured into this overlap. So we have two overlap capacitors. We have a similar one on this side because this is a symmetric device, right? You can switch the order of the gate and drain and gate and source. So I have these two capacitors. So let's talk about the drain gate ones first. So there's a capacitance Cgd, right? Cgd, which is in the pinch-off region is the overlap capacitance. And I have a similar one between the gate and the source. Okay? But let's talk about that capacitor. What else do I have? Do I have another capacitor that I have to worry about? I actually kept the most important one for the last, really. Is there a big capacitor here?
It's oxide capacitor.
The oxide capacitor, right? The channel capacitor is another way of saying it, right? It's the capacitance between this conductive channel and this conductive gate. Forming capacitance. But what is the capacitance? What's the value of it?
There's a lot over Cx.
Well, that's Cx. That's the gate capacitance per unit area, right? That's Cx, correct. But what is the total? What's the capacitance? That's capacitance per unit area. What do you say?
Times the length of the channel.
Yeah, but okay, so times the length of the channel, right? You said this length. Why? The charge is not uniformly distributed on this side, right? So if you want to do it accurately, and we don't even know. I mean, it depends on where it is. So now it's interesting that you can actually calculate this. Exactly. So let's calculate. So how do we calculate it? The total capacitance is basically the total charge divided by the voltage across it, right? So if I want to calculate the total channel charge, that's the first thing I have to calculate for a given VGS. Right? What is that? It's the integral of dq, right, from the beginning to the end of the channel. But what is dq? dq basically it's a charge in a small slice. It's an infinitesimal slice dx. Right? That's Cx W dx times VGS minus VT minus V of x. Right? We did that before. It's over there. dq, the charge in a small slice, is the voltage drop across that infinitesimal transistor, which is the gate voltage minus the voltage here, which is Vx minus Vt, to give you the inversion charge, times the area times the Cx. Okay? So that's the capacitor. Now, I want to integrate this dq from something to something. But if I want to integrate this, I have to integrate over length. And then I have to know the exact location of my upper limit, where the channel ends, which is a function of voltage and all those things. But I also know something else. From the calculations I had before, I know one more thing. I know ID was dq d tau, which we calculated it to be mu n Cx W VGS minus VT minus V of x dV dx, right? Is that the expression you have? Yeah, the third one. Now, I can use this to do something interesting. I notice that I can write dx in terms of dV. Because if I can write it in terms of dV, then I can integrate it from 0 volts to this voltage, to the voltage at the other end of the channel, which is always fixed, which is always VGS minus VT. So then I don't need to know exactly where it is, because I know what the voltage at that point is. So how do I do that? Well, I need to rewrite this as dx is basically mu n Cx W over ID times that times dV. That's right. It's VGS minus VT minus V of x. And then I plug that into this expression, so dq becomes mu n Cx squared W squared over ID VGS minus VT minus V of x squared dV. Now, the good thing is that I don't even need to worry about V of x because it's in terms of V. from whatever 0 to Q channel, and on this side from 0 to what voltage?
VGS minus.
Exactly. Okay, so I have to integrate this, which is relatively easy. So I keep the constants out, Cr squared W squared over ID. Now, what is the integral of this squared? It's this cube divided by 3 with a minus sign, so it's minus VGS minus VT minus D cubed 3 from 0 to VGS minus VT. Now, if I plug VGS minus VT in this thing, it would be 0, right? If this is VGS minus VT, this is 0, so the minus sign goes away, and for 0, it becomes VGS minus VT cubed divided by 3. So this whole thing is VGS minus VT cubed by 3. And ID, I can also rewrite my ID. I can expand ID in terms of VGS minus VT2. So this is mu n, Cox squared, W squared, divided by, what is ID? It's mu n Cox divided by 2, W over L, VGS minus VT squared, times VGS minus VT cubed divided by 3. Right? So these guys cancel that, this cancels that, this cancels that, this guy cancels that, and I'm left with 2/3 Cox W L VGS minus VT. So that's the Q channel. Channel charge. Surprisingly simple expression, actually, at the end of the day. And therefore, the capacitance, the channel capacitance, which would be really dQ dVGS, is going to be 2/3 Cox WL. So it's interesting. It's the capacitance of the channel is 2/3 of the area, the physical channel, of the drawn channel, times Cox, irrespective of the voltage. Which is a good thing, it's a constant capacitance. So in pinch-off region. Now in triumph region, if you were to calculate this capacitance, the channel is extending from the drain to the source. So it's connected to both sides. So the first order approximation that a lot of times is used is that half of this channel capacitance, which in that case would be simply Cox WL, to a good approximation. Half of it is on this side, half of it is on the other side. But in a pinch-off region, which is the region we use most often, this is the expression we use. Now, this capacitance is between the gate and source, right? Because the other end of the channel is only connected to the source, the physical channel. And that's in parallel, in addition to the overlap capacitance. So this is CGS. So we know CGS consists of C overlap plus C channel. And we know C overlap was what? Cox W L overlap plus 2/3 Cox W L. So this is the big capacitor, right? This is the big part, because L overlap is small compared to L. But this is where most of the capacitance comes from. We're a typical Mosfet. Thinking about it, this has some similarities. There's just similarity here to the junction capacitance in the bipolar transistor, and this one diffusion capacitance, the base charge capacitance, CB. Similar to that. These two terms. Okay, so those are my capacitors, and that's my equivalent model for a Mosfet. So I have these 4 capacitors, and I have these 2 transconductors, and the RO. Now, I can calculate one thing. I can actually, let's see if I have a mistake. Now, in a similar way to a bipolar transistor, I can actually calculate the cutoff frequency. The frequency at which the current gain becomes 1 for this transistor. Right? And when you do this calculation, basically, it's an arrangement in which you have the drain kept at some constant DC voltage, and you're applying a constant voltage here. Or you can think about it this way. You're applying an AC current. You don't need any DC current because this can't absorb any DC current. But if you apply an AC current to this and change the frequency of the AC current, and you measure the AC current ID and calculate the ratio of ID over IG. So in the bipolar transistor, this was similar to IC over IB, right? We know what it was at low frequencies in a bipolar transistor. What was it? Beta. What is it at low frequencies in a MOSFET? Infinite, yeah, exactly. Because IG is 0 at low frequencies. With 0 IG, you can use a finite ID. Because it's just a capacitor at very low frequencies. So, unlike the bipolar transistor, where this gain, if you plot it in a bipolar transistor, if you plotted IC over IB, you had a behavior like this versus frequency, by the log frequency. But for MOSFET, it never reaches a plateau. So for MOSFET, it kind of looks like that on a log plot. So ID over IG looks like that. And these are all, let's say, 10 log. And it's a log of frequency. It's a log of 1. We'll talk about this a little more later too. But this was the cutoff frequency. The frequency at which the gain, this ratio became 1. So I want to calculate that. So the cutoff frequency is similar in that calculation. You can easily show that again, the cutoff frequency, omega t, at which, or in other words, when ID over IG becomes 1, the frequency at which this happens, is Gm over Cgs plus Cgd. Remember it was Gm over C pi plus C mu. So this is the equivalent of C pi, this is the equivalent of C mu. So it's a very simple, it's identical calculation. It's actually simpler because R pi is infinite. So you can redo that calculation, setting R pi to infinity, and it gives you the same result. So that's what it is. So let's calculate based on the expressions we have. Now, Gm, we have two expressions for a constant voltage bias. So we have mu n Cox W over L VGS minus VT divided by, now Cgs plus Cgd. So we know this is the overlap capacitance, and this has the overlap capacitance plus the channel capacitance. But we know this is the dominant term. So if you just keep the dominant term, let's see what it looks like. 2/3 mu, 2/3 Cox W times L. Okay? So Cox cancels Cox, W cancels W. You're left with 3/2 mu n VGS minus VT divided by L squared. So that's the cutoff frequency for a standard non-velocity saturated transistor, right? Because I'm using all the expressions I have so far for non-velocity saturated transistor. So what does it tell me? An equation is useful by itself. I mean, unless it tells me something meaningful. I want this frequency to be as high as possible, right? So what do I need to do? Well, one thing it tells me is that, of course, if you have a material, or you can do something with your material to increase the mobility, since this is a mobility control, drift control device, it's fine, right? You can actually improve the cutoff frequency by using something which has high mobility. All right, but that's kind of a tough thing to do. It's kind of a materials problem. What else can I do? It tells me I can use a higher VGS over VT. By the way, we call this VGS over VT the gate overdrive. And we'll use it in circuit design. We see this very often. Sometimes we even show it as delta VGS. Which makes sense. I mean, it's the overdrive over VT, right? How much extra voltage you have in addition to VT, which determines how much inverter charge you have. So it depends on your gate overdrive. And now that directly controls your current, right? So it basically tells you the current that if you want to get the transistor, make the transistor faster, you got to burn more current. So similar to bipolar transistor, right? Remember that? Initially, if you want to make it faster, you have to burn more current. Right, fine. Now, perhaps the most interesting aspect of it, which gave rise to all of this scaling stuff, and we talked about it qualitatively before, is this. So if you want to make it faster, if you have the length of the channel for a non-velocity saturated transistor, your speed quadruples, your cutoff frequency quadruples. Why is that? Well, think about it. There are two things at play here. One is the transconductance. The transconductance is proportional, I mean, for inversely proportional to L. So you have L, you double your transconductance for a given gate overdrive. Right? Now, the capacitance also is proportional to C. To L, I'm sorry, to L, to the channel. So you have L, you have the capacitance, and you double the transconductance. So you have twice as much current to drive half the capacitor. So that's a good thing. That's what gave rise to the huge scaling trend in the 80s and 90s and all that, which basically drove the Moore's law. And still it's going on, but still we are not in that mode of operation anymore. Now let's see what mode of operation we are in. So far, what I've said, where everything we did in our calculation and derivation of the velocity saturated transistor, the non-velocity saturated transistor. Now let's see what changes when you get the velocity saturated. So one thing I know is that my ID in a deeply velocity saturated model, Wn Cox over 2, W E sat VGS minus VT. The first one, right? So that was the expression I derived earlier. Now, if I want to calculate my GM, my transconductance, again, I have to calculate by definition is DID, VGS. So let's see how it behaves now. Well, this is a linear dependence, so the transconductance basically becomes independent of VGS in the first order. So now my gate overdrive does not buy me anything in terms of transconductance if the device is deeply velocity saturated. And in reality, the transistors are somewhere between this and that, these two modes. So by understanding the two extreme cases, we understand where we are. So the dependence is going to be self-linear for most of the transistors that you're using. Of course, it depends on the voltage. So that's my GM. All right. And let's recalculate my FT, or omega T, I guess in this case. 2 pi FT. Which is what? GM over CGS plus CGD, which is approximately GM over C channel. Which is now what? Mu n Cox W E sat over 2 divided by 2/3 Cox W L. Alright, these guys cancel, these guys cancel. So it doesn't depend on the width of the device, which makes sense, right? The FT should not depend on the width of the device. You double the width of the device. It's like having two transistors of the same width in parallel. You have doubled the capacitance, but you have doubled the drive current too. So it's a wash. It shouldn't depend on Cox, because it affects both the transconductance and the capacitance. And what I'm left with is 3/4, that doesn't really matter, does it? Mu n E sat, which is basically nothing but Vsat. The saturation velocity, you can think about it as Vsat. Some constants. And divided by L. So what it tells you is that, well, it depends on velocity, saturation velocity. So if you're dealing with a material, again, it's a materials thing. If your material has a higher saturation velocity, you have a better chance. I mean, your cutoff frequency will improve. But still, it still has this L in there. And that's why we still try to scale the transistors, make them smaller and smaller. Nowadays, we make them smaller not as much to get higher transconductance. We don't get higher transconductance. We scale them to get lower capacitance. And the improvement is only linear, as opposed to quadratic. Because I have the same drive current, I just have to reduce the capacitance by making it smaller. Right. Any questions about that? Yes?
Right now, we know the formula of color frequency of both Mosfet and bipolar cases. Can we get any intuitive explanation to understand why bipolar has higher color frequency?
Oh, that's a nice question. So let's look at that. So for BJT, what was the color frequency expression that we had? So it's the same expression, at least from a small signal perspective. Omega T was GM over C pi plus C mu. Because it approximately is GM, well, over CB at relatively high currents, right? Which was what? Which was GM was IC over VT, and this CB was GM. Well, let's write it this way. Gm, this is Gm tau f. Okay? At high current level, so this is at high current level, this is 1 over tau f approximately. Okay? Now, tau f is what? What is tau f? Tau f is the average time it takes for an electron, let's say an NPN, to get from the edge of the, so this is the emitter, base, and the collector. To get from the base of the emitter, collector, depletion region, to the edge of the depletion region, the edge of the other depletion region, right? The average time it takes for it to go from one side to the other. Now, here, you have a velocity divided by, the transition velocity divided by the length, right? Now, what you need to understand here is what controls these two velocities. What controls this time? What is the mechanism for electron going from this side to that side? It's diffusion, right? It's random thermal movement. Now, we know that electrons move extremely fast thermally. You're basically taking advantage of that really high speed movement of electrons. And the reason they move really fast is that they're very light. So for a given number of kTs, I guess 3 halves, they move really fast at any given temperature. Now, it's random thermal movement. Here though, this, in either case, this case or that case, this is a drift velocity. This is that overlap velocity on top of this thing. Because in a Mosfet, when you turn it on, when you lower the potential barrier, right? We saw that in the energy band diagram. When you're above the threshold, you have an energy band diagram that looks like this. So initially it was high, and then you lower the potential barrier, so it looks like this. So it's N, all across. So there are plenty of electrons on this side, and there are plenty of electrons on that side, and they're constantly going back and forth, right? But there's no net current in the Mosfet. When you apply an external electric field, though, what happens is that on top of this, you have to get that drift velocity, which was substantially smaller than this thermal velocity. And therefore, if you look at these expressions, that's why I said that MOSFETs are not as strong transistors as bipolar. But now, you can make up for that because we are trying to get close to that when you get to restart. That's why we try to make it as small as possible. And that's why we don't drop the voltage. Because if you drop the voltage, it becomes slower. You apply as large a VDS to the MOSFET to actually be operating close to Vsat, which is not exactly equal to the thermal velocity, but it's close. So you try to bring it close to that. But still, you can't quite get there. And that basically goes back to the fact that bipolar transistors are minority carrier devices. The current flow is controlled by the minorities in the base. And here, you have a majority carrier device. So in that sense, this guy doesn't give you as much bang for your buck as this one. Of course, you can try, it depends on L, right? If I make my L really small, then I can get more bang for my buck. But then, what is the parameter that controls my tau f? Equivalent to the L. The width of the base, right? WB. Now, it really boils down at that point to which one of these I can get, how can I get the smallest WB? Right? That's the other parameter that controls. So one parameter so far we talked about is the fact that this is it, you're operating at this is the maximum velocity you can get, which is still smaller than the thermal velocity. So that's in favor of the bipolar. But there's something else. The bipolar, the way they are built, and this is something else I want to talk about. The way they are built are vertical devices. So the width of the base width is controlled through a diffusion process that you can control very accurately. So this is the emitter, this is the base, this is the collector kind of thing. Right? And you control this through a thermal, not this kind of diffusion of the dopants at very high temperature when you fabricate them. Now, you can control this base width, which is a vertical parameter, more accurately than you can control the channel length, which is a lateral parameter. So for a given process technology, typically the way it has been is that you can actually get a thinner base than your channel length by this control. Because you have more control of that vertical parameter than lateral parameter. That also works in the favor of the bipolar transistor. But nowadays, these guys are catching up, right? Because you are trying to make this as small as possible as you can. it's done through lithography. And it's an optical process, right? But think about it. What is the wavelength of, I guess, visible light? Order of magnitude. 400 to 700 nanometers. Okay, order of magnitude of sub-micron, a little less than a micron, right? So it's 0.7 micron, 0.4 microns. Now, if you were to use kind of visible light, what kind of resolution do you expect to get in this lithography process? That's how we make these.
0.2 microns.
Well, not 0.2. I mean, probably on the order of the wavelength, right? Maybe a little less, right? Unless we do something fancy now, then we do a lot of fancy stuff. So that's why we keep going to higher and higher, well, smaller and smaller wavelengths, or higher and higher frequency for the optical wave. So now we're in deep sub-micron lithography. And to do that, we use deep ultraviolet. So that's really limited by the lithography, how fine you can control this process of fabricating this, which we'll see next time, how it's done. So the finer you can make this, the closer you can bring it to this. And that's how they've been catching up. They have finer and finer lithography. And Mosfets today are much closer to bipolars than they were 10, 15 years ago. 10, 15 years ago, there were certain frequencies that were kind of the range of the bipolar that Mosfets could never go to. Nowadays, we're talking about millimeter wave circuits in Mosfets, CMOS. And that's basically because of the fact that you can make these transistors smaller and smaller. It's a technological achievement. Yes?
So the microprocessors, they use mostly Mosfet
Almost exclusively nowadays. I mean,
because of the low input current?
right. That's the base current is one of the killers. The other thing is that in a MOSFET, you don't have the. Okay, so that's another very good question. Why do we use MOSFETs instead of bipolars? You can make bipolar microprocessors, and they would be presumed, and people have made them in the past. But the way it works is that the kind of bipolar circuits that you need to make them fast, are called so-called ECL circuits. And we'll talk about that. It's kind of something similar to that in analog. But they are power hungry. So for every gate you have, and they have basically DC power consumption. So even if you don't switch the gate, you have power dissipation in that node. Therefore, you can't have a very large number of gates. Nowadays, any microprocessor you pick, anything in your cell phone, anything in your computer, anything in there, it's almost exclusively MOSFET because number one, you don't have DC power consumption in the MOSFET gate. And number two is that if you can actually make a transistor, make a bipolar gate that does not have a large DC consumption, but that gate will be very slow. And that really goes back to the fact that the bipolars are minority carrier devices. Because the way to do that is to saturate the transistor. Put the bipolar transistor in saturation. And in saturation, you remember what we had both junctions forward biased. Right? So you dump a lot of minority carrier charge in the base. Now if you want to turn off this transistor, as you saw from your homework problem, you have to let this base charge dissipate. It will take time. Now the more base charge you have, the longer it takes for it to dissipate. So the bipolar gates that you can make that don't have a lot of DC consumption are extremely slow. And there are all sorts of tricks that people did with TTLs and all sorts of things. But still, they are not as fast as the MOSFETs. The good thing about a MOSFET is that no matter how much you overdrive it, if you want to turn it off, you just lower this voltage. And these charge carriers have a place to go. They don't have to disappear through recombination. They can go back to the drain or source, which cannot happen in a bipolar transistor. Right? Because drain and source are n-type region, n+ region. There's plenty of room there for these extra electrons. If you want to turn it off, the electrons go back. If you want to turn it on, they come back in. They pour in from the n+ regions. That's a very good question, actually. I'm glad you asked. Okay, any more questions on this? This is actually very important because this is very fundamental, right? If you understand the physics here, what's going on and what's fundamentally different and what's fundamentally similar in these two devices, you can understand what the trade-offs will be over time. Now there's one more thing I would like to talk about before we go. And that's the subthreshold. That's the last topic on the device physics. And it's kind of a short topic, but I just want to make sure that we talk about it. Now, remember, we said that strong inversion, in everything we said so far, is that we assume that the transistor is off below strong inversion, right? But we know it's not off. We know there's initially, or an NFET, it looks like that. If you don't have any bias, this is EF, this is the channel, and these are the drain, these are the drain and the source, right? You start applying the lower higher voltage to the gate, you push this down, right? And at some point, if you look at EI and EF, then EI and EF will coincide probably. For some, the transistor is still not turned on, technically speaking, right? Because at that point, we are still far away from the concept of strong inversion, which is basically having the same amount of carrier that you had in the bulk before and after. So EI has to be below EF by the same amount that it was above, right? The VF. Now, but if you're at this point, this is the onset of inversion, any kind of inversion, right? But at this point in the channel, if EF and EI are like that, it basically means that it's kind of an intrinsic semiconductor. Right? Anything above this will result. So if I start increasing the voltage, what happens is that I lower the potential barrier a little more, and this will go down. This will go below EF a little bit. Now, this is EF, this is EI. Now I can say I have some excess electrons in the channel. What controls that? We know what controls that. N is going to be Ni e to EF minus EI over KT. Right? And that's the amount of charge I have. And I know my current in the channel. The channel current is proportional to the charge. So it's Q channel divided by tau. Right? The drain current. So the drain current in that region is non-zero because I have charge in the channel of the same kind. I have electrons. I have few of them because of this exponential dependence. Now, but what controls this EF minus EI? But it is the doping, but I'm applying the gate voltage to push this down. Right? Initially it was above. So it's the gate voltage really. Right? So this is nothing but the gate voltage QVG divided by KT. Well, so to a good approximation, this is basically Ni e to QVG over KT. Okay? Now, is it really a QVG? What it really is actually the surface potential, right? It's the surface potential that controls it. So this basically is the surface potential. Remember Vs? That controls how much this changes. But now Vs is related to Vg through a nonlinear expression. So Vg at that point was Vs plus gamma square root of Vs. Remember that? There are two terms to it. This was the potential drop across the depletion region, this was across the oxide. Now, you can capture all of that in this relationship by basically saying, well, it's really it's an exponential, right? So this is a superlinear relationship. So I can relate this to this by saying, well, this is kind of QVG over KT, but then since it is a superlinear basis on that, so it's going to be sublinear in terms of Vg, so this has to be a little bit larger than n. N has to be greater than 1 to count that sublinear dependence. In an exponential, you can do that, right? It just changes the slope. Or like log. So what you have here is something like this. So and this is Ni. And therefore, my current, which is proportional to the channel charge in the subthreshold region, would be proportional to the Q channel. Therefore, will be proportional to E to QVG and Ki. And then you can have some sort of proportionality constants of Is or so. So you can see in subthreshold, actually, the MOS transistor has an exponential dependence on VGS. Right? So it kind of looks like a bipolar. saw that Gm came proportional to square root of ID up there. But below that, it's constant. It behaves more like a bipolar transistor, except for the fact that Gm is low because ID is low. So if you are trying to get an exponential behavior, you can get it out of the Mosfet in the subthreshold region. However, your current level will be very low, the remaining subthreshold region. Okay, so this is it for now for the device physics. Next time, what you'll see, we have two tapes that will basically show you the process, the fabrication process. I thought that they're called silicon runs, so we'll play those. If you have seen them, of course, you can skip it, but they're very good tapes. Actually, they show the two movies, they show the fabrication process. You will see some steps involved in that. And we'll take that, and then from that, basically after that, we'll do circuit design. We'll start our discussion on circuit design. This is a device physics